Okay, you guys, so for our next video, we're going to talk about 3.7, which is finding domains, range, and ranges from graphs and graphing piecewise defined functions. This will probably be the main thing that's new to you. Finding domains and ranges from graphs is something you've been doing for a while in math, but piecewise defined functions might be something new. So let's just kind of review a little bit. So the objectives is we're going to find domain and range graphically or from the graph and graph piecewise defined functions. Okay, so recall the domain of a relation is the set of all first components of the ordered pairs of the relation, and the range is the relation of a relation is the set of all second components of the ordered pair. So this is a very technical term or technical way to say it. Once again, we're going to think about it more as the inputs or the outputs, but there's going to be a new way we think about it graphically. So to find the domain of a function or relation from its graph, recall that on the rectangular coordinate system, this is, what we consider our XY plane, right? This is what we work with. Domain is the set of all first components of the ordered pair, which is the x values. So this means that the x values are graphed. Similarly, the range is the set of all second components in the ordered pair. So this means the y values are values that are graphed. So when you're thinking about domain and range graphically, the way I like to think about it is domain is, and again, this is just a very loose way to talk about it to help you understand. Domain is how far left and right will this graph go or touch? Okay. And then range, for me, again, this is just a loose way to talk about it. How far up and down will the graph go or touch? And again, I'll explain what I mean by this. This is just a way to think about it. In reality, this is the very technical, correct way to say it. The domain is all the x coordinates and the range is all the y coordinates. So when you are finding it graphically, you're basically trying to interpret how many or what x coordinates will this graph be able to touch and what y coordinates will this graph be able to touch. But I like to think about it more like this. So in this particular problem, if we say our domain and our range, okay, so we have this graph right here, the blue line, and the blue line says, or I'm sorry, just so you guys know, I'm talking about this right here, this stuff in green. Okay, this is the graph we're working with. Okay, and this graph shows us that it will go to the left right here. That's where it stops right here at -2. And it goes and it goes and it touches all these x values right here, touches all these x values here, touches all these x values here, touches all these x values. Now, yes, it's going up and down and everything, but we're just talking about x values when we're talking domain. So what x values is this graph allowed to touch? Well, it's allowed to touch everything in between -2 and 4. So I'm going to put my domain to be -2 to 4. Now the catch is that does it actually touch the x value of -2? And does it actually touch the x value of 4? The answer is yes, so I have to use a bracket. Remember, brackets from back in 2.5 tell us that you can touch that actual number. It is actually part of your set. So we are saying that the set from -2 to 4, any number in there, this graph will touch those x values, or it will go through those x values. So range would then be how far or what y values are you allowed to touch. So you're allowed to touch the lowest y value. What is the lowest y value you're allowed to touch? Well, that would be right here. Right here, that's at what, -3. So I'm going to say the lowest value I can touch is -3. What's the highest value I will go to? Oops. The highest will be right here to 4. So I'm going to say 4. And again, it can actually touch those heights. So I'm going to use a bracket. So remember, use brackets for endpoints if the graph touches there. Okay. However, you use parentheses if the graph doesn't quite make it. So a lot of times they'll do this, you guys, you'll see it in another graph we do. It'll do like an open circle here and an open circle here. And then we would have used parentheses in this exact same problem. So again, I want to talk to you guys about it. Look here at the range. You see how right here it's saying this is how far down and up this graph will go. And then for domain, it's saying this is how far left and right this graph will go. So that's what I meant by this over here. That's what I mean by that. That's a way to think about it graphically, okay? So let's look at the next one, okay? Find the domain and range of this relation. So now let's try to use the way I was talking about it, okay? So domain and range. Let's ask ourselves a question. How far left is this graph gonna go? So I'm here and I'm going left. I know I'm going up, but am I also traveling leftward? Yes. How far is it gonna go? It has an arrow at the end. So that means it goes forever. So what's all the way to the left? What's the farthest value to the left? That would be negative infinity. And you use parentheses because you can't actually touch negative infinity. Now we go here. How far right are we gonna go? We're gonna go forever right. So we're gonna go to positive infinity, okay? So that tells us that the domain is all reals. This graph will touch every single X value you can imagine. The domain is everywhere, right? It can go all the way left or right. That's what they're trying to tell you with that blue line for domain. Now the range, you always start from the bottom. You think about what's the lowest value I can go to and what's the highest value I can go to. And again, this is all connected. There's no breaks in our line. This is a continuous function. There's no breaks. There's no hopping around. It's not like doing this and then this and then this, you know. It's not doing line segments and things like that. It's a continuous graph, okay? So we know that our range then, our range is the lowest value, which is right here, and it touches -2. So we're gonna say bracket -2. And then what's the highest value it'll go to? The highest it will ever go is positive infinity. So we use a parenthesis on that. So that's how we can find domain and range graphically, just by looking at how far left and right will this graph go versus how far down to up will this graph go. Let's look at a third example, okay? So domain, once again, let's look. The graph stops right here from left to right. So the farthest left it can go, I'll switch to red because the graph isn't blue. The farthest left it can go is 0. And I'm going to put a bracket because it actually touches a left value of 0, okay? Or an X value of 0. Now, how far right will the graph go? Well, we see it's going like that, and we see it's going like that. So how far right will this graph eventually go? We know that this graph will go to infinity, but we can never quite make it to infinity. So we put a parenthesis symbolizing that we never make it, but we can get so close you can't tell. Okay, you're so close to infinity, you just keep going and going until you get infinitely close, but you never quite touch infinity. Okay, now the range is kind of weird. Let's think about this. I know it's kind of hard to visualize, but the graph, oops, let's do downward first. What is the lowest value, this graph? I know it's going right, but is it also going downward? Yes, so what's the lowest value? We know the lowest value, oops, the lowest value this graph can go is negative infinity. That's where it's heading, right? It's going and it'll keep going. That's what the arrow means. Now I know it's going right, but is it also going upward? So what's the highest value this graph will go? Positive infinity it's approaching, okay? So that's how you can think about it. Graphs with arrows on them, you're oftentimes going to end up with infinity as one of your endpoints, sometimes both, sometimes one. It really depends. But graphs with arrows at the end of them symbolize that it goes on forever in this direction, okay? Let's look at another example. Okay. So this is what we like to call a piecewise defined function. So let me see, they don't actually give a definition of it. So let me go back over here. So basically what a piecewise defined function is it's a function, so it still has to pass the vertical line test, but I oftentimes call them Frankenstein functions because they're made up of different pieces of different functions. So here's a line 3x plus 4, and here's a line negative x plus 1 or plus 2. Sometimes they'll mix in parabolas, sometimes it'll be, you know, absolute values. So piecewise defined functions are different than you think. Think of them more as pieces of other functions, okay? So oftentimes, if you want to graph it, Now, the book shows you a slightly different way. I try to approximate it with my graph. I try to do a good job of estimating it, but then if I need to do exact calculations, I can do those as well. So what a piecewise defined function says is you use this graph when x is smaller than 0, okay? Or if x is smaller than 0. For any time x is greater than 0 or equal to 0, you use this graph, negative x plus 2. So what I like to do is I like to graph. So let's start it at 0. It says 3x plus 4. So I'm going to go down. I'm going to go down 4. Or I'm sorry, I'm going to go up 4. 1, 2, 3, 4. Okay, so this is 4. And I'm going to put an open circle at 0 because notice it has a less than. It's not less than or equal to. It's just less than. So that symbolizes open circle. And then I'm going to graph, or I'm going to do rise over run of 3x. So I'm going to rise 1, 2, 3, and I'm going to run 1 and put a point. So this is the piece of the graph that I'm drawing. Okay. Now I'm going to start this one at 0. Oops. So hold on real quick. That's the graph, but I have to continue it on in this fashion, right? Okay. Now here's the thing. They said, so this is the line, just so we're clear, this is the line 3x plus 4. However, they said they only care about this line if x is less than 0. So I have to erase this. That part of the line is gone. So what I do is I do erasing. I draw the whole line and then I erase the part that we don't care about. Now I'm going to draw the other one for x greater than or equal to 0. So this would be negative x plus 2. So I'm going to go up 2. And this time I'm going to close in my circle because it's an or equal to, right? This says greater than or equal to. So I use a closed circle this time. And I'm going to graph negative 1 slope. So I'm going to go down 1 and over 1. And I'm going to put a line there. Okay. Now, technically, this should be the graph. Right? That should be the graph of this line. However, they said we only care about this line when x is greater than or equal to 0. So I erase that. So I now have, this is what a piecewise defined function looks like, okay? So now let's come over here and try to interpret how to do calculations. When they say f of negative 4, with piecewise functions, you do not use negative 4 in both equations. You have to figure out which one is the correct equation. So here, negative 4, is that to the left of 0 or is that to the right of 0? Well, negative 4 is to the left of 0. And which one of these talks about to the left of 0? That's right, it's the top one. This one talks about to the left of 0. So we have 3x plus 4. So I'm going to use f of negative 4 equals 3 times negative 4 plus 4. Notice I did not use this one. I'm only using the 3x plus 4. Okay. You know what? I'll write it out for you guys. I'll write it in a different fashion. So this is 3x plus 4. And then here I'll do 3 times negative 4 plus 4. So then this would be what? Negative 12 plus 4 would be negative 8. Okay. So we now have the point negative 4 comma negative 8. We have a coordinate. And I know this is a rough drawing, so this won't work out perfect. But if I go down 4, so 1, 2, 3, oh, I'm sorry. I go left for negative 4. 1, 2, 3, 4, and then I go down 8. It's kind of a bad drawing. You guys get the idea, though. It should have been probably a little bit steeper like this. I probably should have drawn my line like this. So this point, negative 4, 8, should be like right here somewhere. And it should have been on the graph. I just can't draw too good. I'm sorry about that, you guys. If I should have had like a grid or a graph paper, I should have pasted to this to help it a little bit. But I hope you guys get the idea. So now let's do 3. So 3, which one is 3? Well, f of 3 goes with this guy. So that means this is negative x plus 2. So then I'm going to do f of 3 equals negative 3 plus 2, which is negative 1. So we have the coordinate 3 comma negative 1. So if I go over 3, 1, 2, 3, let me put that, go over 1, 2, 3, and down 1. There's right there. So that one worked out a little better. That was a little bit better line I drew. Okay. So now let's do this last one. F of 0. Which one of these uses 0? Well, this one says close to 0, but don't touch. So it's not that one. This one says close to 0, and also you can touch 0. So then once again, we use negative x plus 2. So f of 0 equals 0 plus 2 equals 2. So we have the point 0, comma 2, which is this guy right here. So we're seeing that we could graph these points and it would absolutely work, okay? So I just wanted you guys to see this is how you can do, how you can work with a piecewise function. So when they say f of -4, you have to decide which one of these are you going to use. When they say f of 3, which one of these are you going to use? You do not use both in one calculation. You have to decide. So the thing about piecewise is it has domain restrictions. It tells us for each one of these, you have to restrict your domain, what we're allowed to use for that particular graph. And again, I hope you guys can kind of see why I think of it as like a Frankenstein function, because it's a bunch of functions put together, or sometimes you'll see like 3 or 4 even as you go further. So why don't you guys take a minute and why don't you graph the piecewise function, and then also, let me see here, do the calculations for it. And in the next slide, I'll show you like a very organized way you can do it if you'd like, using the actual components or using the actual values. So pause the video and try to see if you can pick some X values to help you draw this, okay? All right, so hopefully you guys graphed it. Started off with your little XY plane. Maybe I'll put some values right away. So let's do 1, 2, 3, 4, 5. Let's do 1, 2, 3, 4, 5. Oh, that's a little close. 5 right there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And again, when you're doing it by hand, it's not going to be perfect because you don't have perfect separation between each of your little tick marks. Okay, so what I'm going to do is I'm going to use f of 0, f of 1, and f of 2, just because that's kind of our common values to help us graph, okay? But I'm going to first do it the way that I showed you above. I'm going to do 3x minus 2. So that is a line that goes, and again, this has the or equal to, so I'm going to use a solid line. So that goes down 2 right here, and then I'm going to rise 3. 1, 2, 3, and I'm going to run 1 right here. So I'm going to draw my line like this. Okay. Now they said this line only exists because of the domain restriction when x is less than or equal to 0. So I don't need this part. That part is gone. So this is the only part that I care about for this particular problem. Okay. Now let's draw the other one. The other one says x plus 3 when x is greater than 0. So I'm going to go up 1, 2, 3. But this time I'm going to use an open circle at 3. And then I'm going to rise 1, 2, 3 up here, and then I'm going to run 1. Oh, no, I'm sorry. I'm talking to myself. So the slope is m equals 1 right here, right? So I'm going to rise 1 and run 1. Sorry about that. And then I'm going to draw my line here, and then I'm going to draw my line here. However, they say we only care about when x is greater than 0. So this part of the line gets erased. Oops. This part of the line gets erased, okay? So that is my piecewise function. Now, the other thing is some people say, well, that's not a function. Well, let's look. If I draw my vertical lines, do I only touch the graph once? The only place I could potentially touch the graph twice is right here. But notice there's an open circle at 0. That way it still passes the vertical line test. So yes, this is in fact a function. Okay, so that would be what our graph looks like. So now the book did it a little bit by calculation. Instead of knowing the graphs, the book actually did the calculations. Sorry about that. So what the book said is let's do f of 0, f of 1, and f of 2. Or they actually did a bunch. And then they also did f of -1. You know what? Let me do it just like them. So f of 0, f of -1, f of -2, and they also did f of 1, f of 2, and f of 3, okay? And what they basically did is they said that when you're going above 0, we're going to use this guy, and when you're going below 0, we're going to use this guy, okay? And if you think about it, that's what they're saying here. This is above 0, this is below 0, or equal to 0. And what they did is when I do f of 0, I have to use this value because x is less than or equal to 0. So when I plug 0 into there, so f of x equals 3x minus 1. When I plug 0 into there, I'm going to get 3 times 0 minus 1, which is negative 1. When I plug negative 1 into there, I get negative 3 minus 1, which is negative 4. When I plug 2 into there, I get negative 6 minus 1, which is negative 7. So I now have coordinates 0, comma, negative 1, negative 1, comma, negative 4, and negative 2, comma, negative 7. So they like to use these coordinates to graph. So we go 0, negative 1. So that would be this guy right here. Negative 1, negative 4, that would be this one. And then negative 2, negative 7, that would be this one. And then they connect the dots. So they do it similar to me, but instead of using y equals mx plus b, they build a little table, okay? Now, similarly, they do that for f of x equals x plus 3. And now, and again, let's look at x plus 3. X plus 3 says x has to be greater than or equal to 0. And these are all x greater than or equal to 0. Okay, so when I plug 1 in there, I get 4. When I plug 2 in there, I get 5. When I plug 3 in there, I get 6. Same as they got. It's the same table, okay? Now let's do our xy coordinates. This is 1, comma 4. This is 2, comma 5. This is 3, comma 6. And once again, just to reiterate, you guys, these are my x's and these are my y's, right? So when I graph 1, comma 4, I go over 1, up 4, that's that point. I go over 2, up 5, that's that point. I go 3 and 6, those are all the points, and they connect the dots, okay? And notice they have an open circle right here. That is an open circle, so it is still a function. If I draw the vertical line anywhere I want, I only touch the graph one time, okay? So this is still a function definitely, okay? So this is a piecewise defined function, and it is defined by separate functions that make it up. So it, again, once again, I call it a Frankenstein function. Remember, when you're doing piecewise, you are only getting one answer per f of value. You can't get two different answers or it wouldn't be a function, okay? So that's gonna do it for this video, guys. Thanks for watching, and see you in class.